In thinking about quantum mechanics and relating the wave nature of particles to kind of the energy, which is the wave nature, to the particles themselves, which have mass and occupy some sort of space, we can locate them in some sort of distinct location, kind of putting all of these things together gives us a picture of the atom, because that's really, as chemists, we want to know where the electrons are on atoms, because the electrons are involved in all the cool chemistry. So if we can understand the energy of those electrons and their location, then we are able to make predictions about kind of what these things, what these different elements, what these different atoms, what these different compounds can do. So chemists spend a lot of time focused on where are the electrons and what are their energies. And so I want to talk today about atomic orbitals. So in a past video, we talked about Heisenberg's uncertainty principle, and we said that the thing that shakes out from that is that we cannot be certain of both the momentum and the position of a particle. And as it gets teeny tiny, then that certainty becomes less and less. Or as I get more certain about one of those factors for that teeny tiny particle, then the other becomes less so. So when I'm thinking about electrons, which fall in that kind of teeny tiny particle realm, when we're trying to describe the location of electrons on these atoms, then we have to rely then on probabilities, right? We can no longer be certain of where exactly they are located, what exactly their energies are, how quickly they are moving. We can't be certain of all of those characteristics together, but we can come up with an approximation. We can come up with where they will probably be, in a probability sense, in a mathematical probability. Not like, oh, they're probably going to be here, right? Like, I'm probably going to have a beer after I make this video. Not that kind of probability, right? These probabilities come from what are called wave functions. And wave functions, in our Greek letters, this is a psi, which is kind of cool looking. It looks like a little trident. And psi squared then gives us the probability of finding a particle within a given area. And so for electrons, when we're focused on electrons because we're chemists, then these wave functions are called atomic orbitals. So atomic orbitals essentially are probability regions in space that give us information about the location, the energy, and the movement of electrons on an atom. Okay, so that's what an atomic orbital is, and that's why they're important. Let's think about this from kind of more of a conceptual standpoint. If I take a hydrogen atom, which we know hydrogen is made up of one proton and one electron. So if I have my one proton at the center in my nucleus here, and I'll use my XY axis, and let's say I have a teeny tiny kind of nano camera, and I'm taking a picture of that one electron as it is buzzing around on this atom, right? So every frame I have a picture of where the electron is located, and then I overlay all of those pictures of where that electron is located. So I'm going to take a zillion pictures, let's say Avogadro's number worth of pictures of this electron, and it's moving around, and we know it's always in motion because everything is always in motion. That's kinetic molecular theory. We can also surmise that the electron more often than not is going to want to hang out closest to the nucleus because it is a negatively charged particle, so there is an attraction, an electrostatic attraction between that negatively charged electron and my positively charged proton in the nucleus. And so I'm taking a series of pictures. Do you guys have one of those like SLR cameras, those fancy ones where you can do action mode? If you have action mode on your camera, and you can kind of get a whole series of pictures. So if I could do a series of pictures for my atom here with Avogadro's number worth of photos, then I might end up with something that looks like this, where the greatest density of my one electron, right, this is a picture, an overlaid picture of my one electron, is going to be closest most of the time to the nucleus, but there's a non-zero probability that it's going to be outside of that range. And if I was to put a boundary around my drawing here, and if I was to say, all right, I'm going to draw kind of the majority of the time it falls within this range, let's say 98% of the time it falls within this range. There's times when it falls outside of that range, but the majority of the time I'm in there around 98% or 95%, kind of depending on my confidence interval there. And then if I'm visualizing this in 3 dimensions, because we live in 3-dimensional space here, and I'm kind of picturing all of these coming out, if we can make one of those like 3D photos, right? So now I have a 3D photo with these electrons, these pictures of electrons coming out in all directions. Now we can kind of visualize this with the middle bit where the electron is most focused. And then as I move outward, there's less probability that I will find it there, but I will still find it within a certain range. And then there's a probability I will find that electron outside of that range, but the majority of the time, a high percentage of the time, I will find it within that boundary. That's really the idea behind atomic orbitals. And this, of course, is a terrible sphere. It looks like a wonky eyeball, but in spite of my poor artistry skills, I hope that this kind of gets at the visualization of what we're looking at here, that this is a region in space where the electron is located. The further away from the nucleus that electron is, the higher and greater its potential energy. And that electron, because it is always in motion, can be found kind of at any given point. I can't say, oh, it's going to be right here, right now, and I can tell you its velocity and I can tell you its position because of the Heisenberg uncertainty principle. We just cannot do that from a measurement standpoint. But I can tell you the region, both energetically and physically, that it is going to be in the majority of the time. So again, this is an atomic orbital. All right, so atomic orbitals come in different styles. There's different orbital types depending on where they're located in the atom, and then also kind of the energy levels that they have. And we'll get into this in a future video when we talk about quantum numbers, because there are quantum numbers that are associated with all of the electrons that are within these orbitals. So the orbital type matters. For the lowest energy type of orbital, these are called the s orbitals. That's what I just drew there with my hydrogen atom. So it's a spherically shaped orbital with the nucleus at the center, and then my electron density is going to radiate out in a spherical pattern. And that spherical pattern, there's really only one orientation you can have, right? If you have a sphere, you can rotate it in all sort of 3 dimensions, but it's always going to be the same orientation. It's always going to be spherical. A sphere is a sphere is a sphere no matter which way you turn it, right? It's always going to be spherical. Now, p orbitals are slightly higher, energetically speaking, so they're a little bit further away from the nucleus. Again, the greater distance from the nucleus that an electron is, then the greater the potential energy. They've been described as bow ties, or you see propellers, or dumbbells is another way, and there's 3 different orientations. If we call this our x-axis and our y, and we have our z kind of coming in and out of the page here, then these guys, again, kind of sort of like I said in the description, we're still going to have a 3-dimensional cloud, so these guys have some 3-dimensionality to them. I always picture kind of 2 balloons that are held together by the knot. So let's give them some 3-dimensionality here. This orbital would be my px orbital. That would be the p orbital that goes along the x-axis. In terms of features, because I have now, I'm no longer just spherical. I have these kind of different shapes. This is called a lobe. So I have 2 lobes in a p orbital. The place where there does not exist electron density, so that would be kind of a place where it crosses the axis, if you want to think about it in terms of mathematical functionality. This is called a node. So we would say that each p orbital has 2 lobes and a node. And in terms of orientation, I have one along the x here. I can have one along my y. So let's draw one up that way. So here's my p orbital again, kind of picturing 2 balloons, and I'm holding them together at the knot. If the knot's at the node there, we can kind of give them some 3-dimensionality too. All right, so there's 2 sets. These guys are all in the same plane. Now, if we have some coming in and out of the plane, so we're going to come in and out of the plane on my z-axis. So this is my py. My z-axis here is going to give me my pz. So if I draw this guy coming back into the page, coming out at you, And again, we can draw some three-dimensionality here. I hope this doesn't get too muddy. Then now we have this guy coming in. So we can kind of picture then 6 balloons that are held together at the knot. My X and my Z are in the same planes. My X and my Y are in the same planes, right? So we can kind of picture these guys all together in one with the nucleus at the center here and electrons in my lobes. So these are p orbitals. If you go a little bit higher energy than p orbitals, we get into the d orbitals. And we're really stretching my artistic abilities with d orbitals, so I'm going to kind of leave that more to your imagination. Where we only had 3 orientations for our p orbitals, kind of the x, y, and z, d orbitals have 5 different orientations, and we'll get into the whys of that a little bit later in future videos. But they don't have a set of a pattern as my p orbitals or my s orbitals do. They tend to have more lobes. So for example, one of them looks like this with 4 lobes along the axes. And this is one d orbital, one orientation. And all of these guys, of course, should be the same size. So forgive my artistic abilities or lack thereof. And there's kind of a larger node space there where the nucleus would be. So this would be one kind of orientation. Again, more lobes, more nodes, more space between. There's a few of these guys that are in a couple different orientations for the d orbitals. There's another one, I describe it as a p orbital with a hula hoop. It's got kind of a large p orbital sort of shape. And then it has a ring around it, which I think it looks like it's a p orbital with a hula hoop. So that's a 3-dimensional little ring. I picture it like an inflatable floaty sort of thing, like in a pool. And then you have your p orbital coming up. This is another orientation of your d orbitals. So it kind of depends. These are all mathematically driven. It looks like it was maybe a 2-year-old who drew them, but these are all coming out of mathematical probability calculations, those chi-squared calculations, which are giving these 3-dimensional regions in space. We go up in complexity from here and we can get into f orbitals. There are even g orbitals and h orbitals, which kind of go beyond most of what we do in chemistry because you get beyond the periodic table when you talk about those. F orbitals get more complicated. Again, they have even more lobes. They have more floral shapes. Some of them have something like 8 lobes, and they get into different varying patterns with more space between them as well. So the ones that we focus on as chemists are S, P, D, and F, and kind of understanding what their shapes look like and understanding kind of the regions of space that they represent and where the electrons are and the energy, and that this is where these electrons most probably will be in a probability sense, is kind of what I'm hoping that you'll get out of these visualizations and not focus on the terrible art, which we can all agree it's terrible. So if you have any questions, as always, don't hesitate to reach out. Otherwise, I will talk to you again soon.